This is our last class, lecture 35. Optimal load flow we continue, and we introduce and finish hydrothermal scheduling. Last time we did with equality constraints, if you recall, the optimal load flow. Today we are doing with inequality constraints. Now, inequality constraints, all of you understand what is the meaning of inequality constraint. It is less than equal to. Now, inequality constraints can be there on control variables, it can be there on dependent variables. Now, these two inequality constraints have to be tackled in two different ways. Let us first consider the inequality constraints on control variables. All right. Control variable is normally specified in control systems by u. So, u min less than equal to u, less than equal to u max, right. For example, power generation, that can be a control variable. You can control power generation by controlling the water gate opening or steam input. So, PGI min is less than equal to PGI is less than equal to PGI max. Now, when you add delta UI to get the latest value of control variable, you check whether this new u new is within these limits or not. This is what you have to check. This must be always satisfied. If this delta u causes ui to cross any one limit, you can either cross the upper limit or lower limit, not both simultaneously. As I have been always saying, you either you are inside the hall or you are outside. You can't be both. Only God is omnipresent. So, then what you do if this happens? Then put ui is equal to corresponding limit. That means either it will be u max or it will be u min. It cannot be both, and proceed, because you cannot have gate opening more than the gate. Suppose you have 10 rupees, you cannot spend more than 10 rupees, that is the upper limit. So, spend 10 rupees only. Okay. So, that means u new will be either equal to u max if the upper limit is crossed, u old plus delta ui is greater than u max, or it will be ui min if lower limit is crossed. If the u new is between the limits, then put equal to whatever is the value you are getting, otherwise OW is otherwise. This should be clear to you. So, u new u will take one of the three values when there is a inequality constraint. Either it will take the upper limit or lower limit or the actual value which lies between the two limits. Now, KT is Kuhn-Tucker conditions. I hope you have by now mastered these Kuhn-Tucker conditions, because we are applying them again and again and again. What do these conditions tell? Please read them in appendix E of any one of the books. They say these are only necessary conditions, not sufficient. I have already explained you what is necessary condition and what is sufficient condition. For you to pass the course, it is necessary to appear in exam, not sufficient. You have to do well, you have to get certain amount of performance. So, this is the meaning of necessary and sufficient conditions. So, the necessary conditions are the first order partial derivatives of Lagrangian with reference to all the dependent variables should be 0. After that, then using those necessary conditions, you write gradient, and these are, that is why I am not repeating KT conditions here. Now, this is a gradient, because after all those Kuhn-Tucker conditions, you get the values that we have seen last time. You substitute the Jacobian, put the value of lambda, and ultimately you get the value of gradient, and gradient should be 0. But that was the case when there are no constraints, no inequality constraints. But with inequality constraints, gradient get modified into 3 parts. It should be 0 if everything is within limit, like last time. But if you have put ui is equal to ui max, then gradient should be negative, less than equal to 0. Or if ui you have put u min, then gradient should be either positive or 0. This is called semi positive definite and semi negative definite, which you must have done in control systems. I do not know whether you have read control systems or you have forgotten. So, gradient vector should satisfy these 3 conditions as and when there are constraints on inequality constraints on control variable. It was so easy to handle inequality constraints on control variables. But if you have inequality constraints on dependent variables, then what do? You can't do the same thing. You can't put that equal to x max and x min. You have to do something else. What? We have to talk about it now. X has to be between x min and x max. What is x? Let us say voltage on a PQ bus, which is not a control variable because it is a dependent variable. On a PQ bus, what are control variables? P and Q, that is given to you. What is not given to you is V and delta. So, V becomes a dependent variable. So, we must lie at each bus between a given minimum value and given maximum value, handled by penalty function method. This saying one of the ways. Now, in this class I cannot talk about all the different ways, but the best way to handle constraints on inequality constraints on dependent variables is by using penalty function method. Now, what is a penalty function method? That means I am treating them as a soft constraint. It is not like gate opening. You cannot open the gate beyond limit. Okay? It is a soft constraint. Like a class, I can always finish beyond 5 minutes. You won't mind if I take extra 5 minutes. But exam, no extra 5 minutes normally given. You have to submit your, especially an IS exam, an Indian Engineering Services, or any important CAT exam, JE exam. Nobody says, okay, take extra 5 minutes. Nobody, you will be hanged. Tomorrow it will be headlines, particular center 5 extra minutes were given, so cancel the exam. So, that is a hard constraint. That means when I say penalty, it means I allow certain deviation, but I penalize. It is like a book. If you want to, if you fail to give back the book to library on that thappa date, I do not know whether nowadays any high tech thing is there. In our days there used to be a thappa. Thappa means 15th December. So, you have to either deliver the book back before that time or at the most 15th December. But suppose you have exam on 16th and you give the book on 17th or 16th, he will at the most charge you some penalty, some 1 rupee fine, or he will give you some piece of advice, do not do it again. That is a penalty. Now, that means the original cost CXU now get modified by adding the penalty cost. This is called penalty cost. So, now you have to minimize the original cost, fuel cost plus penalty cost. You can't give penalty as much as you want. Can you deliver the book after 1 year? No, he may take the penalty almost the cost of the book. It is better to purchase the book rather than give a penalty for 1 year. So, this penalty does not mean you can have any amount of penalty cost. No, this has to be a part of minimization process. So, C dash is a new modified objective function, original objective function plus cost function. For violating jth inequality constraint, this is the cost Wj. All such constraints summation j. So, total penalty cost is sigma j Wj. All variables will not cross limits, otherwise there is something wrong with your definition of limits. Okay. Suppose you put your limit so stringent 0.99 per unit to 1.01 per unit, all the PQ bus voltages will cross the limit, because you have foolishly kept such a limit which is not possible in India, because voltages go minus infinity to plus infinity. So, you have to at least put 0.9 per unit to 1.1 per unit, then it is likely that some of the variables, voltage variables, will not cross the limit. So, j, that is why I put it here j, otherwise I would have put all j. This is the graph which is very important to understand. Y axis is penalty cost, x axis is the x variable. If it is between x lower bar means x min, there was no place to write min, so I have written x lower bar. X upper bar means x max. Why upper bar and lower bar are not normally used? Because it can be misunderstood by vector sign, and even lower bar some people write for some special meaning. So, I write x min, x max where there is no confusion, but here because of the space constraint, let me use the word constraint, I have put x lower bar and x upper bar. If they are between these two limits, no problem, this dotted line which is a rigid limit, no penalty, penalty is 0. The moment x crosses either the upper bar or lower bar, this quadratic curve is there. So, penalty starts increasing moment x crosses limit, and as it moves away from the limit, the rigid limit, the penalty also increases. The penalty cost characteristic you can choose. It can be quadratic, it can be cubic, it can be exponential. Suppose you are very strict. If you give book after 10 days, you can say you are suspended or 1000 rupees. So, that is a very stringent penalty, right. This is the model I have chosen. Wj is equal to gamma j xj minus xj max whole square, gamma j xj minus xj min whole square. Luckily, one of the two will be there, as I have been repeatedly telling you, either it crosses upper limit or it crosses lower limit. You can't have both. So, it crosses upper limit, this equation. If it crosses lower limit, this equation. And gamma j is called penalty factor, not power factor, but penalty factor. It is up to you to choose what penalty factor you want. I will comment on this, the selection of gamma j, after some time. Why I put square here? Penalty cost should be positive. You cannot have negative penalty. You cannot give an award for someone for not giving book in the proper time. Okay, no problem, well done, here is 1000 rupees for you. I think nowhere, no library will give you reward or award for depositing book late. No appreciation for that. Hence, we have to have a positive penalty cost. So, square. Now, the necessary conditions or Kuhn-Tucker conditions gets modified. You get this Wj also terms here, which is quite understandable, because the Wj is definitely a function of x, because the Wj is on x. Naturally, u it is 0, there is no penalty on u. So, whenever u is concerned, it will be 0. So, these are the modified Kuhn-Tucker condition equations. Now, you have to solve them, and again same gradient vector, consider your necessary condition, gradient should be 0 within certain limits, within epsilon. If 0, optimization has reached. If not, use this gradient to find out u new. U new is equal to u old plus alpha times gradient. Alpha is again a scalar. We have already commented on alpha. How do you select alpha? I promised you that I will comment on gamma j. What is gamma j? Gamma j is nothing but penalty factor. If you want full name, I have given you that beautiful example of IIT Delhi coming from Ames to Qutub Minar, that oscillations I explained you. Similarly, this penalty factor, it is for an analyst, for a control engineer, for an energy engineer to choose the value from past experience. Past experience always helps you. A doctor, he must have taken such patients several times. He must have operated the Professor Trehan, heart operation number 1 in the country. He must have operated some several thousand bypass surgeries. So he has a vast experience behind him. So he knows how to take corrective action in real time if something goes wrong. That's why everybody wants to be operated by him only, which is not possible. So everybody cannot be taught by, let's say, Professor Siddhartha Roy. He may be the best teacher, but then he has his own limitation, constraints, right? Everybody may like to go USA, but there is a constraint on H1B visa. Everybody wants to go and do some job there, but there is somebody should be willing to take you. You can't land in JFK airport and say, give me a job. They'll say, go back. So penalty factor, if you choose a very steeper value, so what will happen? It will very stringent value. It will remain close to limit. The rigid limit I have plotted that vertical lines. So it will remain close to them, but convergence there are problems. Convergence down. You know, share market, the news it shows which shares have gone up, which shares have come down. Even in chemistry, you must have used this arrow. If there is a precipitate, then down arrow. If it is a gas, it is, I don't know whether you remember chemistry. I remember. I read chemistry in 61. It's more than 44 years back. The year when Mughal Azam was first released in black and white version. So my chemistry teacher used to tell me that when it is H2 hydrogen, show arrow. He will give extra mark, teacher, because that means you are telling him, look, I know H2 is a gas. So gas means, or precipitate, then down. So this down shows the convergence becomes poorer. If I choose a lower value of gamma j, not a higher value, then what happens? Solution is away from the limit. Suppose I converge at 1.5 per unit voltage, what the hell? What sort of solution you have got? How can I have a 50% extra voltage, over voltage? So what is then what one should do? The remedy is, the prescription is, start with a lower value and slowly increase it if you are not getting convergence. And there are several methods available in literature, as and when you do your master's thesis, doctoral thesis, involving choosing the penalty factor, then I can tell you, even if I am not your guide, to which paper you should refer to. And remember, this can be used in any area, biotechnology, nanotechnology, biology, physics, because optimization is everywhere, constraints are everywhere, medical. So you have this topic is universal, like reliability. Everybody needs a reliable operation, whether it's engineer, doctor, manager or lawyer. You choose a lawyer which will win you the case. Nobody chooses a lawyer which you lose the case. So you always ask what is his record, track record, how many cases he has won. OPF we have just finished, optimal power flow or optimal load flow. Where do you use it? You use it in all system planning and operation. All the time you need this data and optimal data. You just don't need values of PQV delta. You need the values of PQV delta which are the best as per some given condition, as per some given situation. So optimal load flow, you need to run all the time, whether it is a planning operation or whether it is a system operation, real time, online. So you have to have a software ready in any power utility, whether it is a power grid or it is a NTPC or it is a IPRI in US, Electric Power Research Institute, where you can all go, or BPA or Department of Energy, various institutions. You need to have this software. Well, gentlemen, now we come to the last topic of the last day, and it is very important for our country and for several countries where there is a mix, hydrothermal mix. If you have pure thermal, no problem. If you have pure hydro like Norway and Sweden, no problem. But if you have a mix like India, Australia, Japan, even US, there is a bit of hydro, then you need to find out how much hydro and how much thermal. Scheduling means you have to schedule the amount of hydropower generation and amount of thermal power generation to satisfy a given load. As I have been telling you right from the first day, in India we have 72% thermal, 24% hydro, 3% nuclear and 1% renewable, for which you are doing your MTech. It's largely in renewable energy sources, but that 1% is very important, because that is what 1% is. We should become 10% by 2020, and it is the hope of all villages where there is no grid. Even nuclear can be modeled as thermal. So you have to find out, only the fuel cost is different. It may be uranium, it may be thorium, it can be plutonium. Even in thermal, it can be coal, it can be oil, it can be gas. If it was always only thermal, then it is what? It is very easy to optimize. Why it is very easy to optimize? Because it is a static optimization. What is static optimization? It is irrespective of the time you are optimizing. Suppose I am carrying out optimization in Indraprasth power station or Badarpur power stations. How many units are there? 5 units. Alright. As long as coal is same, the coal cost is same, labor cost is same, no pay commission has come, your scales are same, your salaries are same, your maintenance cost is same. Whether you solve this problem in January, October or November, the answer will be same. So it is a static optimization problem. The period doesn't affect the final outcome. But if it is a hydrothermal problem, it's more complex. Why it is more complex? A period is involved. Why period is involved? You are using a water, and water availability over a given time period. It can be a day, it can be a week, it can be a month, it can be a year. We don't go beyond a year for operational problems. Planning problem, yes, we can go 10 years, 20 years, very short term planning, short term, mid term, long term and very long term. See, we are already started saying that 2020 will be a developed country. So for that we have to work. It won't become automatically, oh 2020 1st January has come, or today onwards we are developed country. It won't become like that. We all of us have to strive, we have to work, our GDP should improve, our per capita energy consumption should improve and so on. Whatever are the parameters to be called oneself a developed country, like Singapore is a developed country now. So fuel cost is 0 as far as water is concerned. So availability water consideration makes it a dynamic optimization. That means you are working for a given period. And dynamic optimization problem is always more complex than static optimization problem. We still try to minimize thermal cost with respect to constraints. What are the constraints? Main constraint is water constraint. Two types of water constraints: storage, Bhakra, reservoirs, inflow, how much inflow is available, that is the data of course. So, depending on this we have to minimize over a given period. Period as I said can be day, week, month, year. Here is the simplest possible hydrothermal system drawn. Why simplest possible? It has to have at least one hydro station, one thermal station to justify calling it a hydrothermal system. That is why it is called a fundamental hydrothermal system, because you cannot go below this. Here is a thermal power station, here is a hydropower station, here is a load, this is a PGT, power generation by thermal plant, PGH, power generation by hydro plant. This will, you will now learn how to specify suffix, prefix, subscripts, why G, G generation, why T, T is thermal. You can't just write any one of ABCD here. So, this makes sense. P is power. So, power generation by thermal power plant. This is a hydropower plant. This is J is inflow. Universally J is used as a inflow. X is a storage, and this is the water discharge Q. So, here is a turbine which generates power and power goes to the grid, water discharge. The control variable here is water discharge, gate opening, which you know anyway because of AGC. You must have done hydrothermal system in AGC. Let me tell you one more thing. Hydropower plants are of three types. We are interested in storage type because the optimization is only possible in storage type. The second one is pondage type, and third one is run of the river. Here we are not considering small hydro which is renewable. No, this hydro is also renewable, but small hydro is normally considered in our non-conventional energy sources below 15 megawatt. 1 to 5 megawatt is mini hydropower plant, below 1 megawatt is micro, and below few kilowatts is nano, and nowadays is an era of nano, everything nanotechnology. The idea is whatever power you can generate is welcome, because power is a commodity which is in short supply, at least in developing world. Storage is something where you can really apply optimization. What is pondage? Water is coming all the time, but you can't control it. You can't. Why you can't control it? You can't store it. It's coming, so you put a turbine and generate power and feed it to the grid. But there is no control there. There is no optimization there. This is a bonus. It's not a salary. You get a bonus once in a year and use it the way you want to use it. It helps to improve your condition, lifestyle. Run up the river is as and when water comes, use it. Like a daily wage, as and when he gets offered to come, he comes to IIT every day at 8 o'clock. Oh, today you are not required, sorry, he goes back, he goes somewhere else. So, as and when there is a snow melts, water comes, use it. If it is not there, don't use it. The hydrothermal optimization problem is divided into two parts: short term, long term. Short term is a day or a week. Long term is a month or a year. As I told you, operational problem cannot be considered for more than a year. There is no sense. Like we give a timetable semester wise. Tomorrow somebody will ask, what about 2007? What will be the timetable like? Is there for you full? 2007 is far off. Even 2005 first semester timetable is not yet given. Why we want to divide into two parts? Somebody may ask, normally you don't ask questions, but suppose you ask me questions. Okay, what is the great issue about it? Why don't you call it same, whether it is a day or a month or a week or a year? It's a hydrothermal optimization. No, the constraints change. If it is a day long problem you are solving, the head is likely to remain same. You treat a constant head. Bhakra head will not change drastically today, the 23rd of November. Today is 23rd? Yeah. At 5 am, whatever was the head, it is likely to remain same, more or less. It is so huge reservoir. But for a month, head can change. So, head variations must be taken into account if you are solving long term problem. You may perhaps ignore losses when you solve a day long problem, but in a month long, year long problem, you can't ignore losses. And here I am not talking about only PL, that is transmission line losses. I am also talking about seepage loss, water seepage. In your hostel rooms, maybe better rooms, but in some of our houses there is always a seepage. The walls are always wet. Given data, initial water storage, suppose you are solving a year long problem. So, 1st January, what is the water storage you know. End of the year, what should be water storage you also know. 0th is beginning, N is final. Initial water storage and final water storage is given to you. So, within that, what I am specifying? I am specifying the water availability, how much water you are entitled to use. For example, storage is shown by X, this is time. January, this is the water storage X0. This is the water storage in the January of 5. That means this is the water I can use provided there is no inflow. If there is inflow, you have to consider that also. That is an additional bonus water availability. Of course, you are given inflows and power demand, they are known. Out of these 4, these 2 chaps are random variables. I hope you must have done enough of stochastic control in your undergraduate and postgraduate, at least you have done it, which is very important topic. Truly speaking, in life nothing is known with certainty. Which grade you are going to get in this semester, nobody knows. You can only make a guess. It may be a correct guess, because you know minor 1 marks, you know minor 2 marks, and you are likely to perform. But again, it is a function of type of paper, it is the type of examiner, the examiner's mood on that particular day, and so on. So, it is a random variable. When do you get a telephone call? Nobody knows. Suddenly tring. Of course, nowadays cell phone means all the time it is on. So, you can predict every 1 minute you can get a call. But the landline call, you really don't know when it will come. Customer in a shop, when customer will come, nobody knows. A death, though it is a certainty, but when it is going to come, I don't think anybody knows. So, water inflow and load, these 2 are random variables, and if you consider them random variables, then the problem becomes stochastic scheduling of hydrothermal system, but I am going to consider only deterministic. Stochastic maybe next time, because it is very interesting and very fascinating to deal with stochastic problem, because then you have to minimize expected cost, standard deviation, the moments, they all come into play. The best book in this case if you want to learn random variables is Populus, and that's a wonderful book, Random Variables and Stochastic Processes. Control variable we have chosen is Q. Objective function is minimization of Ct, integral 0 to t c dash pgt d dt. T is the total period, day, month, week. What are the other constraints? Total power generation thermal plus total power generation hydro minus loss minus demand should be 0 within this time period, 0 to t. I think you know this thing. If it is square brackets including 0 and t, if it is a small bracket leaving that final point, both small 0 and t both are not considered. So, you know these things. Water availability. The final water storage minus initial water storage must be equal to total input minus total output. I hope this is clear to you. This is the reservoir. Let us say month of August. In the beginning of August, this is the water storage. The end of August, this is the water storage. During August, this is the inflow, and outflow is or discharge is Q1. So, X1 is equal to X0 plus input minus output. This is called water continuity equation, which you must have done in control system, plant equation. Yeah. So, water availability is this, and hydropower is defined as head into water discharge. But if you want total equation, it is a function of storage and water discharge, I will give you an exact equation after 2 minutes. But nobody solves now problem in continuous time variables. All of you must be intelligent enough to understand by now, since you are using computers, we discretize the problem, because computer won't take continuous values, you have to discretize. That means you have to have a sub interval. If it is a day, 24 hours, divide into 8 parts, 3 hours each. If you are more fussy, 24 hours, 1 hour each. So, optimization interval T is divided into n sub intervals. Week 7 days, month 30 days, year 12 months or 365 days or 52 weeks depending on what you want. We assume that in each sub interval variables remain fixed in value, otherwise it is very difficult to handle the problem. If I am considering 1 month as a sub interval, during that month inflow is constant, outflow is given, the water storages are given anyway in the beginning and the end of the period, otherwise there will be chaos. So, now the problem is you want to minimize delta t times the cost with reference to the control variables q n, and this can be delta t can be absorbed in C dash. So, C P G T n, n is during nth interval, thermal power generation during nth sub interval, maybe a day, maybe an hour, maybe week, maybe month, and so on. What are the constraints? Power balance, this is our old friend, total power generation. Why there is no sigma here? You are just talking about one thermal power station, one hydropower station. If you say what is this? This is not practical. All right, you have here I, you have here J, as many hydro stations, as many thermal power stations. So, without loss of generality, I have written here power balance equation. Water continuity equation I have just explained you using that plant equation model. So, water storage at the end of nth subinterval minus at the end of n minus interval is equal to J minus Q. If you transfer it to left hand side, then you will get this. Now, if you convert the units of storage into discharge units, then you get rid of this delta T, because if you divide by delta T, x meter cube becomes meter cube per second, cum x. So, they all become in the same units, and hence I have written this xn minus 1 minus jn plus qn is equal to 0, n is equal to 1 to n, and PGHN. This is the equation I promise you that I gave you in hydropower equation. So, what is this hydropower equation? It needs slight explanation. Hydropower generation is equal to head into discharge. Okay. Head is an average head and discharge is useful water discharge. So, average head is this. If the storage varies, convert into the head unit, take average, add to 1, this is an average head. H0 is a basic head. What is basic head? If this is reservoir, this is penstock, this is your turbine, then this is your basic head H0, and then depending on the water storage, head varies. This is what I have done. H0 is a basic head, 1 E is a conversion unit. This is explained in the book also, you can see the book, and Qn minus rho is effective water discharge. This rho is non-effective water discharge, means it includes what? Seepage, evaporation. You can't stop water evaporating because sun is there. In some countries where water is a scarcity, like your Middle East, they have developed a substance, a solid which you put in a water, the evaporation rate gets slowed down. It was shown on TV day before, but still it can't be 0. If I eat anything, I am definitely adding calories, even if it is a diet coke, even if it is a low salt, low calories stuff, right? Only bread, no butter, no bread pakoda. Still that bread itself is a food and I am adding to it if I eat. So, this subtract non-effective discharge. So, this is the equation which is used throughout the world for hydropower generation. The proof of this, the derivation of this is given in the book. Since time is limited, I am not able to take it up here. However, you are free to read it if you so desire. This is again a water availability equation. Final storage minus initial storage minus summation of all inflows plus summation of all discharges must be 0. Final minus initial input minus output. So, this is a water availability equation. Now, as usual, you formulate your Lagrangian. How do you formulate your Lagrangian? I have been talking last several lectures. Original objective function, augment it by all the constraints multiplied by dual variables, adjoint variables, Lagrange variables, lambdas. So, first constraint is power balance equation, lambda 1n. Second constraint is water continuity equation, lambda 2n. Third constraint is water power generation, hydropower generation. And then apply your Kuhn-Tucker conditions. Differentiate with respect to all the dual variables, Pg, all dependent variables rather, and then calculate gradient. Gradient means control variables. What are the control variables here? Only water discharge. And then see if it is 0. If it is 0, you converge, you optimized. Print out data, what is hydro generation, thermal generation, loss, storage, discharge for your benefit. This is what is happening all the time where hydrothermal operation, DVB, Damodar Valley Corporation, Bhakra, authority there, or wherever there is a Tata have hydro stations also near Koina and others. Now if there are constraints, inequality constraints on control variable, treat them in the same way as we have treated in optimal load flow. What do? We equate it equal to Q max or Q min. Q is the control variable. So if Q crosses certain limit, you equate it, because you can't have water gate opening beyond a limit. So you have to equate it equal to Q max. Or if there is a minimum water discharge limit crossed, then you have to equate it equal to minimum. Why? You may need water for something else, irrigation, flood control, navigation, drinking, washing. Water is a multi-purpose job it does. And continue. And the gradient vector doesn't become only 0. It becomes more than equal to 0 if it is crossing the lower limit. It becomes less than equal to 0 if it crosses the upper limit, like we did today itself. Now if there are constraints on dependent variable, storage, well, penalty function method. Now there will be several penalty function here because there are several dependent variables. Water storage is a dependent variable. Thermal generation itself is a dependent variable. So you have as many penalty functions. Now their terms will appear in these Kuhn-Tucker conditions. Calculate the gradient, again see whether you satisfy the optimality conditions or not. That is the 3 conditions: gradient 0, gradient positive or 0 for lower limit, gradient negative or 0 for upper limit. And then that's the problem is solved. You can instruct your operator, look, operate at this value, operate at that value, and you get optimal hydrothermal solution. If there is a nuclear also, well, that's again you can model it like a thermal power plant. Again it is a cost equation, and normally nuclear is used as a base power plant, so it really does not participate in the optimization. What you do, you subtract that nuclear power generation from load, and the load, modified load, is to be supplied by hydro and thermal. But if you are a fussy, if you are very sticky, no, I want optimization. So include it in this cost function here, plus C of PGN nuclear. Then you may change this N to M as I have done in the book. You will wonder why I have used here superscript as M, because N may be used as a subscript for nuclear power generation. So to avoid confusion, both ways N, superscript N and subscript also N. What is this going on? So to avoid that confusion, in fact I have used in the book not N but M as a superscript. M means during mth subinterval. So gentlemen, we come to an end here. All good things come to an end, though we like to continue, but then constraint, and this is a hard constraint. Today is perhaps our last lecture. So I enjoyed talking to you all this semester. Hope you would have also enjoyed it, and I wish you all the best for your exam on 27th. And this is not the end, this is only the beginning. We'll continue to have our association wherever you are, through email or whatever, IT technology. Any difficulty you have so far in any lectures, whatever I have delivered, you're most welcome to ask now. There are 3 minutes, or you are welcome to contact me wherever I am. Either I am in this office or house or wherever. And if you have anything, please let me know right now. Otherwise, yes, regarding numericals, there is one numerical solved in the book. You can read it. Normally you need a computer to solve a hydrothermal power problem, even if one hydro and one thermal. So I'll appreciate someone can develop a program on MATLAB and see whatever I have solved the problem is okay or not, whether it converges or not. So if one of you can do that, if you feel there is no time here, you can do it after the exam just for your satisfaction. The algorithm works or not. You will feel happy if you get the same results which I have got it. Anything you want to say? You are our guest. No questions, no queries. Exam will be my 13 marks question. It may be chota 2 question or one big question. The main thing is marks will be 13 and the time required will be 1/3 of 2 hours. That is 40 minutes. But you don't have to, it's not a rigid constraint. You can do my portion in 30 minutes, save those 10 minutes and put it into other teachers' questions. Okay then, all the best.